So what we're going to do today is we're going to look at some trends that you can see on the periodic table. So just a little review. If you guys take a look at your periodic table, you should see that elements in the same column, they have the same number of electrons in their valence shell, their valence orbital. Now, if you guys forgot what valence means, it's just the outermost. Okay, so I'm going to do a quick pop quiz with you guys. If you take a look at beryllium, how many valence electrons does beryllium have? Yeah, 2. Okay, yeah, the peace sign, just 2. Okay, so what that means is everybody in this column, magnesium, calcium, strontium, barium, radium, they all have 2 valence electrons. Now, again, the exception is going to be this middle area, the transition metals. There is no pattern for the valence electrons, but everything else follows that pattern. Because remember, these guys can have different most common ions. They can also form multiple ions. Okay. Now, this is important because valence electrons are the ones that are involved in bonding. So when atoms get into relationships and they get married and stick together, the valence electrons are the things that stick them together, okay, not the inner electrons. Okay, and then we also learned before that when an atom becomes an ion, you do that by adding or removing electrons from the valence shell, okay? Any questions about just the review information? I know it's been a while, I think about 2 units since we went over this info, but any questions? Okay. All right, so let's do a couple practice problems just to see if you guys really have questions or not. So what I want you guys to do is take a look, or on your paper, you can look at the person next to you, and I want you guys to find the total electrons and the valence electrons for all those atoms up there. Okay, so we got potassium, helium, chlorine, and then you got some ions on the bottom. If you can't see the charge, let me write it a little bit bigger. This one is K plus, S2 minus, and Cl minus. Okay, so take about a minute to do that, and then we'll go over it before we get into the actual meat of the unit. All right, maybe another 20 seconds. Alrighty, guys. So if you guys are still finishing up, feel free to finish up the ones you are doing, but I'm going to start going over it for those of you that are done. Okay, so we're going to take a look at potassium, helium, and chlorine first. So these ones should be pretty easy. We just need to look on the periodic table. So we have potassium. How many total electrons does potassium have? Yeah, 19. It's just an atomic number, same as the protons, right? So potassium is going to have 19 total. Okay. And how many valence electrons? Yeah, 1. It's in the first row of that first box of that row. So there's going to be 1 valence electron. Okay. Pretty easy, right? Okay, next one is helium. Okay, how many total electrons does helium have? 2. Yeah, the atomic number is 2, so it's going to have 2 total. And how many valence? 2. Because if you look, this one's the weird one, right? There's only 2 boxes in the first row. So there's going to be 2 valence electrons. So helium only has 1 shell, and it only has 2 electrons in that shell. That's the total. And then we have chlorine. I'll just give you guys chlorine. Chlorine is pretty simple, 17 total. And then we're going to have 7 valence electrons. Okay. Any questions about those? Hopefully those weren't too bad. All right, now we're going to look at K+. Now K+ is an ion. And so what we need to figure out first is, did it gain or lose an electron? So if you take a look at K, regular K, okay, it has 19 total. If I go to K+, do I gain or lose an electron? Yeah, lose. That's how it becomes positive, right? It's like you ditching Mr. O from your life. Your life gets a little bit more positive. So K+ is going to have 18 total. Now, K only had 1 valence electron, right? So we got rid of the valence. So if I get rid of the valence, how many valence electrons do I have now? Yeah, 8. Good. Because what happens is potassium has 1 in the 4th shell. If I get rid of the 1 in the 4th shell, this 3rd shell becomes the new valence shell. Okay? So just make sure you guys understand that concept, because if you don't understand that concept of the valence, that if you lose all the valence electrons, do you lose the shell? It's going to get a little bit harder to conceptualize some of the things going on. Okay? So if I lose all the valence electrons, the previous shell becomes the new outside shell. Okay. All right, let's go to the next one. The next one is S2 minus. So S is sulfur. So regular sulfur has 16. So if it's -2, did I gain or lose electrons? I gained, right? So I gained 2. So I go from 16 to 18. Okay, so sulfur is going to have a total of 18 electrons. Okay, and how many valence electrons will S2 minus have? 8. Good. Alrighty, and then last one, I think you guys probably got this one. Cl minus is going to end up with 18 total electrons. Oop, not total, and 8 valence electrons. We just go from here, and then we gain to get to the next box. Okay. All right. Any questions about those problems? Okay, so if you take a look at it, a bunch of atoms can have the same number of electrons and valence electrons. The only difference now are the number of protons in the nucleus. Okay. Okay, so that's very important, because what we're going to be talking about is something called effective nuclear charge. Okay, it's a mouthful. So ZF. Okay, so the symbol that we use to describe or represent it is the letter Z, and then we put EFF for effective on the bottom right. Okay, ZF. Oh yeah, my name's F. Yo, 21 Jump Street's on Netflix. Yeah, do you guys see it? Dude, it brought back so many good memories. Such a stupid movie. And if parents are listening to this, I do not endorse that movie, but it's pretty funny. Okay, so the ZF, basically what ZF is, it tells you the average, basically like electrical energy that an electron feels. Okay, so how strong an electron is connected to the atom. Okay, now before I talk about the factors, let's just take a look at this example right here. Now, if you take a look at this phosphorus atom, you guys see how there's electrons in the outside shell, right? Now, these electrons in the outside shell, they feel a different connection to the nucleus than, let's say, an electron on the inside shell, right? Because obviously the electrons on the inner shell are closer, and so they're going to feel a stronger pull, right? But if you take a look at these electrons, the things that determine that attraction is going to be these two things. The number of protons in the nucleus, and the symbol for that is Z, which makes sense, right? More protons means more positive energy, means it pulls the electrons in tighter. Okay, but the other factor that affects this is the electron repulsion, right? Because we said that electrons don't like each other, right? Electrons push each other away. And so what happens is, as the nucleus pulls the electrons in closer, right? The nucleus, let's say, is a very good-looking man, right? And then the electrons are these pretty ladies. And as the good-looking man attracts this lady in, this lady that's closer is going to be like, nah, that's my man. It's going to push this electron away, right? I'm sure this is a common experience that all the guys in this room experience, right? And you ladies as well. Got to kick those guys away. But anyway, as the protons in the nucleus pull the electrons in, the other electrons push those electrons away. Okay, and that's why we call it chemistry, right? Yeah, what's up? Yeah, so all of these electrons feel a different attraction to the nucleus, right? And that attraction depends on how strong the nucleus is, right? Because if there's more protons, that's more positive energy, that's going to pull the electron in. But if there are more electrons around the nucleus, it's going to push these electrons away. So it's kind of like a balancing act. The protons are going to pull the electrons in, the other electrons are going to pull them out, and it's kind of like this weird balancing act of attraction to the nucleus. Does that make sense? Yeah. Guys, I'm practicing my dad jokes. Are they pretty good? They're good. I appreciate that, guys. But it sounds like a lot of pity laughing. Anyway. All right, you can take that pity laugh outside. Anyway, so we can calculate the ZF, okay, and we can do that by subtracting the Z, which is the number of protons. So the Z is the number of protons, and the S is going to be the number of inner electrons. Okay, so let's do an example together to calculate ZF. So we're going to calculate, I'll do carbon with you guys, and then you could try sodium. Okay, so let's try calculating the ZF for carbon. Okay, so what we need to do first is figure out how many protons carbon has. How many protons does carbon have?
6.
6, yeah. It's going to have 6 protons because that's the number on the top of the box. Okay, so that's Z. The Z of carbon is 6. Now we need to subtract the inner electrons. Now, what I'm going to do is just to kind of show you guys what carbon looks like. Carbon is going to look like this. There's going to be 2 shells. There's going to be 2 electrons on the inside because the inner shell is, the first shell. And then we're going to have 4 on the outermost shell. So S is going to be all of the inner electrons. How many inner electrons does carbon have?
7.
My goodness. It doesn't even have 7 electrons. 2, yeah, the ones in the middle. Okay, so it's going to be 2. So phosphorus, for example, has multiple inner electrons. If you guys take a look at this, this is phosphorus. Phosphorus has 10 inner electrons, 2 in the first shell, 8 in the second shell. And so that's going to be the S for phosphorus. So basically anything that's not a valence electron is an inner electron, and that's how you can find S. So what's the ZF for carbon?
9.
My goodness, Molly. I'll get you a calculator for Christmas. Yeah, it's going to be 4. The ZF for carbon is going to be 4. See, it's that mob mentality. Somebody just says something, I'm like, oh, that must be right. Alrighty, guys. So I'll give you guys about a minute to calculate the ZF for sodium. Okay.
22.
Don't listen to him. He's a false teacher. Are you talking about the quadratic formula?
Yeah, I totally forgot it.
You know how I memorized it? It's you have to sing it or to the tune of Pop Goes the Weasel. X equals negative b plus or minus the square of b squared minus 4ac all over 2a.
Yeah, no.
Bro, I remember that from 7th grade because of that song.
I never got that word. I always confuse myself.
Use that song, guys. It'll stay in your memory forever.
Do I want it to stay in my room?
You do. Quadratic formula is very useful. Alrighty, guys. Let's find the ZF for sodium. Okay, so let's what's the Z value for sodium?
11.
Is it 11?
Yeah.
I can't even tell if you guys are trolling anymore. 11. Okay, we have 11. And then how many inner electrons does sodium have?
22.
10, because we have 2 in the first shell, 8 in the second shell, which is going to be a total of 10. So what is the Zeph for not carbon, sodium? Yeah, 1. My goodness, Molly, I'm about to kick you out of the classroom for lying. Okay, so it's going to be 1. All right, makes sense? All righty, for sure. So that's the Zeph value. Okay, so before we're gonna talk about that again in a second, but before we do that, we want to figure out what ions look like, different atoms. So we learned about how to draw shell models for regular atoms. However, and we learned about most common ions. However, we didn't talk about how to draw most common ions. Just a little review from what we knew before. Atoms, they don't like having incomplete shells because it makes them unstable, right? They want to fill up their shell. So whatever shells they have, they want to make sure it is completely filled up. All the slots are taken. And what they're going to do is they're going to try to fill up that outermost shell with electrons, okay, or by kicking out electrons. And that's going to make them into an ion. We learned before that the MCI, most common ion, is the ion that the atom wants to be. And so what we're going to do now is we're going to practice drawing shell models for most common ions, okay? So here are the steps if you guys need it. But let's start with sodium. I'm going to practice with sodium, and then I'll have you guys try one on your own, okay? Okay, so I'm going to draw the regular or the shell model for regular sodium. So we're going to write Na in the middle. How many shells does sodium have? 3, yeah. It's on the 3rd row. So sodium is going to have 3 shells. So sodium has 3 shells. Now what we're going to do is we're going to fill up the shells with electrons. So if we look at sodium, sodium is going to have 11 total electrons. So it has 11 total electrons. So I draw 2 in the first shell because the first shell can hold 2. That's 2 boxes. The second shell can hold 8. So I'm going to draw 8 right there. Okay, now I've used 10. So we're going to plug in 1 more. And that is going to be 11. Okay, so that's what regular sodium looks like. Okay, now we need to figure out, is it easier to fill up or empty the outermost shell? So what do you guys think? Is it easier to fill up that 3rd shell or to just get rid of the electron? Yeah, get rid of it. Okay, so basically just opposite of what Molly says. Okay, we want to lose 1. Okay, if I lose 1 electron, remember, we always have to lose the valence electron. So if I get rid of this electron right here, are there any more electrons in that valence shell?
Yes.
No. So we're just going to get rid of that. And there you go. We have sodium's MCI, and this is what sodium's MCI looks like. Okay. And that's pretty much it. Now, if I wanted to draw the Lewis structure, all I would have to do is write Na plus and draw 8 electrons around it because that's the number of valence electrons it has. Yeah, what up?
So if you were to have maybe like silicon, would it be better to would it be better to, because it's like basically half to half, would it just be better to fill it up all the way? Or?
So we said silicon, though silicon and carbon are an exception. What are the MCIs for silicon and carbon? Anyone remember? It's no MCI. They don't have MCI. So they don't like to form ions. Instead, they're gonna create some other type of bond that we'll talk about in the next unit. Yes, what a great. Oh, Lewis structure, we only draw the ones on the outside. So since Na plus only has 8 valence electrons, we just draw the 8 on the outside. All right, any other questions? Okay, I'll have you guys try 8-4. Maybe you guys can see it. I'll leave it at 8-3 just so you can take a look at it. But I want you guys to draw the shell model for oxygen's MCI. Okay, so take about, I don't know, minute and a half to do oxygen's MCI. After that, we'll go over it and then we will move on. We talked about most common ions, right? Okay, just making sure. It's been so long. Good. Good, good. I love avocados.
They're good. But
Yeah.
they're so pricey.
They are.
I would say guacamole or Chipotle.
Yo, all I want in life is to be able to buy guac at Chipotle without having to worry about it. That's all I want in life. But it's so expensive, and it's like the price keeps going up. Back when I was in college, it was like 70 cents for guac. Now it's like $1.50.
It's like two.
Yeah, and my income has not gone up double. Still can't afford guac.
That's a really good place. Really spicy and you won't pay cash. But or heading westward.
What's it called?
Your watch that idea. That's Taqueria Mexicana.
Mhm.
They only accept cash. The tacos and like the meat's so good.
Is it?
Yeah.
I'll check it out.
What?
Zacate le dice zacate.
No, taqueria.
Is that a bad word?
No, zacate is grass.
Oh, so
Touch grass.
Well,
that wouldn't be a bad name for a taco place.
Sounds bad.
no, yeah, zacate like grass-fed cows.
Yeah, exactly. Exactly. Alrighty, guys, you guys ready to go? Okay, so oxygen's MCI. So let's just talk about the charge. What is oxygen's MCI? What charge does it want?
Negative. Positive 2.
-2, exactly. So we have -2, which means it's going to gain 2 electrons. So regular oxygen is going to have 2 shells. And so what we're going to do is we're going to draw the normal 8, and then we just need to add 2 to it. So this is regular oxygen. Okay, it's going to be 8 electrons, and then we just need to add 2 because this wants to be O2 minus. So we just do that, and just make sure you put a 2 minus next to the O, and that's going to be the shell model. Okay, for the Lewis structure, we just put O2 minus and put 8 around it. Okay, so it looks basically the same as sodium. The only difference is the number of protons in the middle. Okay, make sense? Alrighty. There was another one where I was going to do neon and I was going to sing John Mayer's Neon, but I'll spare you guys that, okay? So let's move on. Nah. Hey, I know what I'm good at, and singing is not one of those things.
Neon. It wouldn't change.
Huh? It won't change, yeah. Okay, so before we move on, just to clarify, I want to make sure we all know the trick for MCI. Everybody here is +1. Everybody here is +2. The guys in the middle, they don't have an MCI. This is going to be +3. This is no MCI. -3, -2, -1, and also no MCI. Okay, so if you guys don't have that written down somewhere, just make sure you guys refer back to this. This is a pattern that's going to be very helpful when you guys are taking the AP test because you don't have to calculate what the MCI is. You should just be able to look at the periodic table and figure out what the MCIs are. Okay. All right, so I'll leave that up there for just a second. Okay, but what we're going to talk about now is something called electronegativity. Okay, so electronegativity, I know it's at the very corner. I'm just leaving it up here so some people can copy down the chart. But electronegativity is how tightly an element holds on to its electrons. Okay, so we talked about before how the connection that an electron feels to the nucleus, the Zeph, it's going to depend on how many protons there are and how much shielding there is, right, with the other electrons. Okay, now we kind of combine those things, the Zeph thing, and then we call it electronegativity. Okay, and so a couple things are going to determine how electronegative an atom is. Okay, electronegativity depends on, first and foremost, if it's an MCI, if it gained or lost electrons. Make sure you guys jot this down somewhere because it's kind of like a step-by-step process that we can use to follow, follow which one is more electronegative. Sorry, I had a brain fart. Okay, so the first thing that we want to talk about is the MCI. Yeah. Oh yeah, let me write the pattern for you right here. +1, +2, +3, no MCI, -3, -2, -1, no MCI. Yeah, that's the pattern on top. Yeah, you might have it written down somewhere from old notes. I just put it up there for like review real quick. Okay, so the first thing you want to see is it an MCI? Second thing you want to see is the number of shells because it's going to determine the distance from the nucleus. And then the third thing you want to see is the number of protons. Okay. All right, so let's do the first one together, and then I'll have you guys try the other two on your own, okay? So we want to figure out which element is more electronegative, sodium or lithium. Okay, so first we want to look at, hey, is it a MCI? So if we take a look at sodium and lithium, are they ions? No, it's just sodium and lithium, so we don't have to worry about that one. Okay, now we want to take a look at the number of shells. How many shells does sodium have? Yeah, 3. Okay, so 3 shells. And how many shells does lithium have?
2.
Yeah, 2 shells. Okay, so let's think about this logically, okay? Sodium is holding the electrons at 3 shells distance. So it's like over there, okay? Lithium is holding it only at a 2 shell distance, so like over here. Okay, if I was holding my phone at 2 and 3, which one is it easier to steal from me?
3.
Yeah, 3, when it's further away. So the further away the electrons are, the less electronegative that atom is, okay? So let me write that down. So more shells is going to be less electronegative, right? Because the electrons are further away, right? So guys, when you're trying to pursue a girl, you want to keep her at a close distance. Because if she's too far away, some other stud's gonna come and steal your girl. And so electronegativity, the further away it is, the more shells it has, the less electronegative it is. Yeah. Yeah, so the protons do affect it, but the distance is more important. Yeah, there's actually a formula that we can take a look at. It's the E equals Q1, Q2 over distance. If you guys look back at old notes, you guys can look at that, but the distance plays a much bigger factor than the protons. Okay. Okay, the way I like to think of it is you're a buff dude or a buff girl, right? It doesn't matter if you can lift 300 pounds or 100 pounds, that distance is what's more important. Yeah. It doesn't matter how strong you are, exactly. It don't matter how strong you are. Another cowboy farmer from Wisconsin is gonna steal your girl. Or cowgirl, I don't know, whatever. Anyway, I'll give you guys about 2 minutes. You guys can try B and C. I want you guys to go through that process, the 1, 2, 3 process, to figure out which one of the two is more electronegative. What? What about me? Yeah, dude, that's why I call chemistry. Got my degree in chemistry. Got a degree in dating. I'm not a matchmaker. I'm an instigator, and I just make fun of you. Yeah. It's a gift that I had since junior high. When my friends liked a girl and they were talking to each other, I would just pants them and run away. Pants my friend, not the girl. Just need to make sure I clarify. That was like the 2 biggest things when I was in junior high and high school: pantsing and ball taps.
Oh.
Yeah. Dude, it was crazy, man. We would like pants my friend, and then one other guy would come and ball tap him, and we'd just run away. Other times, 2 people would just ball tap and run at the same time. You know what a ball tap is?
I don't know either of those.
Good. You've had a great life.
Well, I mean,
We had table
not
tops.
really, but I mean,
Wait, it's
I
not
don't know what those 2 things are.
Pantsing is where you pull their pants down,
Oh.
and then ball taps are where you on their, the male genital area, and it's excruciating pain. And it's not about strength; it's about the whip in your wrist, because it has to be like a little tap, and those are the ones that hurt the most. Bro, I saw a guy throw up one time because he got all tapped so hard. It's in 8th grade, Mr. Clifton's PE class.
So specific.
Yeah, dude, it's a traumatic memory. I've never seen a man be in that much pain from a ball tap. No, it wasn't. I wasn't the perpetrator.
Were you the victim?
No, I was more of a pantser. One time I did pants someone and I got both things. I got the underwear too, and that was pretty bad. Huh? Yeah, this is being recorded. I'm sorry, parents. I do not endorse any of this. Pantsing and ball tapping is bad.
We got in middle school, like 6th grade. I don't know why, but there's a whole thing of pantsing, right?
Yeah.
And then someone ended up pantsing like 3-4 people at once. I'm like,
Wow, what a stud.
But the PE teacher was right there, and it's just like, oh.
Yo, the real challenge is to pants the PE teacher. Probably shouldn't do that though.
Tabletop.
Guys, this is not an endorsement to pants anyone, and don't pants me. Just want to make sure I get that clear. Okay, you guys ready to go? Or are you guys still working on it? Ready? Okay. All right, let's go over B. So we have fluorine and beryllium. Okay, so if we take a look at fluorine and beryllium, neither of them are ions. So let's look at the shells. How many shells does fluorine and beryllium have? Yeah, we got 2 for both of them, right? They both have 2 shells. What that means is we need to look at the protons. How many protons does fluorine have? Yeah, 9 protons. And how many protons does beryllium have? 4, right?
Wait, beryllium. Oh my god.
Yeah, beryllium has 4. Dude, I don't even know if you guys are messing with me now. I was like, wait.
I got it wrong.
Okay, so we got 4 protons. Okay, so let's think about this logically, okay? All right, we'll do it the other way now for the ladies. Okay, ladies, your man is close to you, okay? Or there's you and another girl. The man is an equal distance to you from the other girl. You are stronger. You are 9 protons. You can lift 9 protons. The other girl can only hold 4 protons. Who's gonna get the dude? Which lady? 9 or 4?
9.
Yeah, 9. The stronger lady will get the man. And you know what? If he can't handle you being strong, he's not good enough for you, okay? Okay, women should be strong too. My wife is freakishly strong. Anyway, what was I saying? Oh, fluorine. So yeah, so which one is more electronegative, fluorine or beryllium? Fluorine. Okay, so fluorine is more electronegative. Here we said that lithium is more electronegative. Okay, so fluorine is more electronegative, and the rule for that is going to be more protons is more electronegative. Yeah.
I have a question.
Yeah, what's up?
Were you always the one that was lifted up and she was the one that was always carried?
No, she's not stronger than me, but like she's pretty strong, man. Like there was one time, like after we got married, we were like play wrestling, right? And you're like ah, and I tried to like not really use my strength, bruh. I couldn't move her, so I had to like really put my hips into it. I was like, ugh, like pivot. Yeah, what's up? Oh, it's right there. It's the goggles on the side. Yeah, I know, dude. I had to legit judo roll her, dude. She's so strong. It's scary, man. But anyway, I think ladies should be strong too. All right. So let's bring that together. I'll have you guys do nitrogen and sulfur. Do you guys do nitrogen and sulfur already?
Yeah.
Wow, you guys are so fast. So nitrogen, how many shells? 2 shells. My gosh. How many shells does sulfur have? 3 shells. Okay, this one's pretty easy. Which one is more electronegative? Yeah, nitrogen. Okay. What's up, Mr. Pepeek?
What's up, buddy?
Are you peeking at our class notes?
I am peeking at your class.
Yeah. Peking duck?
Yes. 2 shells, 3 shells. Man, they're learning patterns.
They are.
Patterns are fun.
Numbers.
Yeah.
Did we do this in my class?
Yeah.
We did trends in my class when I taught. You remember that? No, what?
I don't.
Did you do that last year?
Yeah.
Okay, and I probably.
Alrighty, guys. So let's kind of figure
So you
out
don't
a
want me to keep
pattern.
talking, I guess.
No, I want to talk. That's why I became a teacher, to listen to myself talk. I go home and listen to these videos again. That's weird. No, I'm just kidding. I don't. I really don't like my voice. I would prefer to have your voice. It's more
Oh,
baritone and deeper than mine. I still
Jeez.
sound like I'm going through puberty. They've heard my voice crack before.
I believe that.
Dude, I lose all authority and all like,
Okay, kids.
Yeah. I'm like, everybody be quiet. Anyway, so let's figure out, let's see if we can figure out a pattern using the problems that we just solved. So sodium and lithium, we said lithium is more electronegative. Okay, so if we take a look at the periodic table up here, we said lithium is more electronegative than sodium. So that means that as we go up the periodic table, is it going to get more or less electronegative? Yeah, more electronegative. Okay, so that we got that right now. And then we said for the previous problem that which one is more electronegative, fluorine or beryllium? Fluorine. So that means that as we go to the right, does it get more or less electronegative? Yeah, so that's going to be your pattern that you guys can use to do it quickly. Okay, as you go up and to the right, wait, that's your left. You're to the right, it's going to get more electronegative. Okay, so just make sure you jot that down somewhere. It'll be a quick way for you guys to figure out the answers to these problems. Okay.
Which element is most electronegative?
Helium.
Helium has no electronegativity, so to speak. Yeah. Because it doesn't bond. Yeah. There's no gases don't bond, but you're in the right spot. What would be the first one after that? What's that? No, almost.
Lithium.
We'll go up and over to the right.
Oh.
Right.
Fluorine.
No, remember neon can't have, the last column can't have any electronegativity.
Oh.
Yeah, fluorine.
Very good.
Dude, Mr. Pepic is stealing my. I had a joke for that.
Oh, Jesus, I'm sorry.
I had a. You ruined my joke.
I'm out of here.
Oh my gosh. It's
I'm
okay.
leaving. Can
It's
I hear
okay.
the joke though? Most EM,
Yeah, electronegative.
that's the joke.
No, it's. I was gonna ask them, what do you think's the most electronegative? And then they were gonna say helium, and I'd be like, no, it's not. And then they would say hydrogen or neon, and I would be like, F. It's the most.
I like that. I'm gonna steal your joke.
See, now you're gonna do it in your class,
They can't-
and they're gonna think you're a comedic genius.
I'm a comedic genius. I steal
You
all
are a
my material
comedic
from you.
genius. I steal a lot of material from you too.
Which one is least electronegative? Come on, wave the right flag, people. You give up? Did you like that one?
Oh wait.
Wave the white flag, kids, if you want to give up. Francium, yes, because France always
Fails.
waves the white flag. They always surrender.
I don't know the French.
That was a good one too.
I just made that one up because I was like, maybe I need to give you a joke, so you can use that one with them. not them.
Well, now you used the joke. All right, guys, which one is most? I'm just kidding. All right, so that's the pattern for electronegativity. Okay, so let's go to 8.8. This will be your big test for electronegativity. I want you to get all five of these, five of these elements, and I want you to organize them based on their electronegativity. Is this spam?
Yeah.
Dude, wait, did you hang up?
Yeah, I did.
Oh,
Guys, I am the best spam responder
You should make it. You should make
because I have perfected my Korean accent. And I just talk to them in Korean and then ask them if they want to pick up their dry cleaning. And I just throw in all the other Korean stereotypes like gaming, eating kimchi, eating dog, asking them if there's stray pets in their neighborhood, telling them that as soon as I moved in, no more stray pets. And then they get really confused. And I think they usually hang up first.
In my mom's country, they eat guinea pigs.
They eat guinea pigs? Hey, food is food, man.
Where's your mom?
Food is food.
Ecuador.
Yes, food is food. I don't judge, man.
Oh yeah, I see people eat like crickets and stuff. It's good.
Dude, everybody eats like random animals. And that's okay. As long as it don't make you sick, it's okay. Huh?
So that
Okay.
So racist.
It's not though. You wanna know a funny meme that I saw? It said, this tweet encapsulates 2020. And then somebody tweeted, This is if somebody woke up from a from a coma and asked me how 2020 went, I would say somebody ate a bat and now I don't have a job. But anyway, a lot of evidence is coming out. It's not from a bat though. That is from it's man-made. Yeah. But I don't know. But there is a lot of evidence coming out.
Question on your expertise.
Yo, I can't talk too much about it on video because YouTube is gonna put that COVID-19 like banner underneath the video. Then it's like visit the CDC, and it's like the person legit is just like, oh, I'm locked in a pandemic, and then all of a sudden there's like that banner underneath. Okay, I don't want to get that on this video. I know, bro. They're already running ads on these videos. I need that YouTube ad money, man. Yeah, no, I'm just kidding.
How many subscribers?
51.
Actually, hold on.
I'm just kidding. Guys, I'm not doing this to make money.
We're doing it to make money.
We're supporting our
Huh?
educators.
Yeah. Oh, like who's subscribed? I can, but I'm not going to. So I don't want to expose the nerds out there, you know? Gotta protect the nerds' identities. I am subscribed to myself. I made 51 fake accounts to subscribe to me.
Boom.
Anyway, are you guys all done organizing electronegativity? Sorry, what was that? 8 point. Yeah, we're doing 8.8 right now.
There's a reel on here.
Yeah. It's a demo that I did yesterday. Oh.
Fire.
Yeah.
I like it.
Do you guys want to do it? Oh wait, I give Mr. Edwards all of it. Never mind. We'll do it later.
Yeah, so
Actually, you know what, guys? During our break, I will set it up and we will run the reaction just so I can show you guys. I have to go to Mr. Edwards.
education.
Edumacation. All right, I'll give you guys maybe 20 more seconds to finish organizing, and then we will. Let's take a break, and then we'll do the next one, and then we'll be done for today. Ah. Hey yo, if this does get that COVID banner, please let me know, because I think that'd be the funniest thing in the world. Because apparently they put subtitles on these videos now. It's like auto closed captioning.
Really?
Yeah, it's pretty amazing. The technology. No, electrons don't matter too much. No. On any of the shells. Just look at the shells and then protons afterwards.
You can make money off of closed captioning. It's not bad, but then you have to like watch the whole video.
Alrighty, guys, let's organize these in terms of least and most electronegative. Alrighty, guys, so I have all of the elements here. The first thing I want to look at for all of them are the number of shells. So how many shells does Y have? 5. P? 3. How many does N have? 2. Cl?
3.
And F?
2.
Okay. So we already started putting them in terms of electronegativity. So I'm going to go from the least to the greatest. So we already know that F is the most electronegative, right? So we're going to put it furthest away to the right because that's the most electronegative. Okay, now we said for shells, if I have fewer shells, is that more or less electronegative? Yeah, more electronegative. So less shells equals more electronegative. Okay, so we said fluorine's already the most electronegative. So which one out of these is the next most electronegative? Nitrogen. Yeah, nitrogen is the next most electronegative because it has the fewest number of shells. Which one of these is the least electronegative? Yeah. Yeah, Y. Okay, and that's because it has the highest number. Okay, so phosphorus and chlorine have the same number of shells. And so we have to look at the protons. How many protons does phosphorus have? 15. And how many does chlorine have?
17.
Okay, so which one of these is, okay, so which one of these is less electronegative?
Phosphorus.
Yeah, it's phosphorus. Dang, you guys are good at this now. I'm trying to trip you guys up. So there you go. That's the order. You can also use our going up and to the right method. I just wanted to show you the justification behind it. But if you did that method, that's fine too. Okay, you probably won't get an FRQ asking you to show your work for this. Yeah. Yeah, so not in terms of like organizing from electronegativity, but they start incorporating these into FRQ questions and stuff.
They usually mix that.
No, they're not going to ask you to show work for this. Yeah,
You have the same glove as the setup right from Power Ranger.
sure. Okay, let's take a 7-minute break. If you need to go to the restroom, go to the restroom. I'll start setting up that demo real quick. And then in 7 minutes, we will go over the last topic for today. Alrighty, guys. So let's go on to the next topic. The next topic is going to be atomic size. And we're going to be looking at both neutral atoms and ions. So these are the 3 things that you guys need to keep in mind when you guys are determining the atomic size, which is how big an atom is. Okay. Number 1 thing the most important thing is the number of shells, because that's going to tell you the distance from the nucleus. Okay, the second most important thing is the number of protons that atom has. Okay, which makes sense because if there are more protons, it pulls the electrons in more, which makes the atom smaller. And then the number of electrons is important because electrons push each other away. And if you push the electrons away, it's going to get bigger. And so those are the 3 things that you guys want to take a look at when determining atomic size. So I'll give you guys a minute to jot that down. After that, we'll try 8, 9A together, and then I'll have you guys do B on your own, okay? I'll give you about 30 more seconds to copy down the 3 important steps you want to take a look at, and then we will try some practice problems together. They are bankrupt. They got shorted into the ground.
It felt so sad to see their last message on their website before they shut it down.
Yeah.
It's so weird because then you can still see like the parts where like it was like in the side.
It was just really, like take down that freaking IKEA. Put down everything.
Yeah. Amazon killed retail. But also Toys R Us had a bad business model and the stock market, they got shorted. Nice. Alrighty, guys. So let's try part A, and then I'll have you guys try part B on your own. So we got beryllium and barium. Okay, so this one's pretty easy. First thing we want to do is look at the shells. How many shells does beryllium have? Yeah, it's going to have 2 shells. How many shells does barium have? Yeah, 6 shells. Okay, so this one's easy. Which one is bigger? Yeah, barium is bigger because it has more shells. Okay. Now we're going to take a look at one where they have the same number of shells, and let's see if you guys can figure out which one is bigger. So we got phosphorus and sulfur. So take about 30 seconds to try that out. Phosphorus and sulfur. Which one is bigger? I neutralize it. I neutralize it. Light hydrogen gas is lighter than the air. Yeah, it's fun.
Because when you think about it, we're breathing in like matter. No,
We are. You're getting hit by matter everywhere. It's like you just can't feel it.
Yeah.
but it's also thinking, I don't know, thinking about it, it's like, oh,
Alrighty, guys, let's go over this one. So we got phosphorus and sulfur. Shh. How many shells does phosphorus and sulfur have?
3,
Yeah, they both have 3 shells. Okay. How many protons does phosphorus have?
15,
Okay, 15 protons. And how many protons does sulfur have? 16. Forgot what I was gonna say. Okay, so let's think about this. Which one of these atoms pulls in the electrons more? Sulfur pulls it in more because it's 16 protons, right? It's a really good looking atom. It's pulling the electrons in. Phosphorus, a little bit more ugly. So phosphorus is going to be bigger because it can't pull the electrons in closer. Yeah, it's a 15 out of 16. Almost there. All right, so there is a pattern for the atomic size as well. And so we're going to take a look at the periodic table. So we said that barium is bigger than beryllium, right? So as we go down, does it get bigger or smaller? Bigger. And then we said phosphorus is bigger. So as we go to the left, does it get bigger or smaller? Bigger. So this is the exact opposite of electronegativity. As you go to the left and as you go down, the atoms get bigger, which makes sense because electronegativity is how tightly it holds the electrons, right? The tighter it holds the electrons, the closer the electrons are going to be, right? And so it's just going to be the exact opposite of that. Okay. Any questions about atomic size? Yeah, what up? Bigger. They get bigger as you go to the left and down. All right, guys, so this is completely off topic, but we're just going to do a quick demo that I did for my other classes. I wish we had time to do this with the lab in this class, but alas, we cannot. Can you hold this? Hold it out. Okay, so inside of the balloon, we got some hydrogen gas. And so what we're going to do is we're going to react it with the oxygen that's in the air. Who's scared of loud noises? Not you? Good. Yeah, if you're scared of loud noises, just cover your ears. Yeah, you can get off the tank test. Yeah. Then people are gonna go to sleep. That wake you up.
Keep the lights off.
Yeah, so that's the reaction between a hydrogen gas and oxygen gas.
Do you keep the lights off?
No, you're gonna go to sleep. I'm getting sleepy already listening to myself talk. Okay, so let's we did the trends. Now I'm gonna put you guys to the test. But this one is harder because we're going to be taking a look at MCIs as well. Okay, so I'll give you guys 3 minutes for this one. If you guys can get this, I think you guys have really mastered this concept. I want you guys to organize these elements from smallest to largest. So smallest on the left, largest on the right. Make sure you guys use all 3 of the principles we talked about, the number of shells, protons, and electrons. And hopefully you guys are able to get this, okay? Good luck, guys. Alrighty, guys, maybe just another minute to finish it up. Ionization. Huh? A meme? A meme? Meme? I'm looking forward to seeing the meme. Sure. I love chem memes. Alrighty, you guys ready to go?
Yes.
Alrighty, so let's start going over it. Okay, so the first thing that we want to look at are the number of shells. Okay, so hydrogen, potassium, and bromine are pretty easy, right? How many shells does hydrogen have? Yeah, one shell. How many does potassium have? Yeah, 4. And how many does bromine have? Yeah. Okay, so the regular one's pretty simple. Now we got to look at the MCIs though. Okay, so what's hydrogen's MCI? What's the charge on it? Yeah, +1. Okay, so regular hydrogen has 1 shell, and so hydrogen looks like this. Okay, with 1 electron. So if I lose the electron, how many shells does H+ have? 0, exactly. It has no shells because it only has 1 electron. If I lose that electron, it has no electrons. So if there's no electrons, there are no shells. Let's look at potassium. Potassium is K+. Now, potassium only had 1 valence electron. So if I lose an electron, how many shells does K+ have? Yeah, 3. And then lastly, bromine. Bromine's MCI is Br-, so it gained an electron. So regular bromine has 7 valence electrons. So if I gain 1, how many shells does Br- have? 4. It stays the same, exactly. Because all it does is it gains 1 electron in the outermost shell, and then there's going to be 8 on the outside. Okay, so that's going to be the number of shells. Hopefully you guys are able to get that. And this allows us to start putting them in order. Okay, so which one of these is the smallest?
H+.
Yeah, H+, because there's no shells. What about the next smallest? Yeah, we got regular H. Okay, what's next? Yeah, K+. Okay, and then for the rest of them, we need to do a little bit more work because they all have 4 shells. Okay, so let's go to the protons now. How many protons does potassium have? Yeah, 19. How many does bromine have? 35. And what about Br minus? 35, yeah, exactly. Okay, so we have 19, 35, and 35. So between the 19 and the 35s, which one is smaller? Yeah, the 35s will be smaller because potassium has 19, so it's not able to pull in the electrons as much as the bromines. So that means potassium is going to be our biggest one. So we're going to have 2 blanks, and then we'll have potassium as the biggest. Okay. All right, now we finally have to look at the electrons. So bromine, regular bromine has 35 electrons. How many electrons does Br minus have?
36, and therefore bromine MCI is going to be bigger than the bromine.
Spoilers. Okay, so 36, right? And exactly like Molly said, if there's more electrons, what do electrons do to one another?
It makes it repulsive. So
They push each other away, so Br minus will be a bit bigger than bromine. If you guys got that, great work. That was a tough one with a lot of different concepts. I didn't even go over the electrons in the practice problems. And so if you guys did that, pat yourself on the back. Alrighty, guys. So that's going to be it for today. Yeah, what's up, Great? Yeah, more electrons makes it bigger because the electrons push each other away.
Think about the area to be
I got so
covered,
happy
how much
about that. Because the median circuit that you said 35, and then oh my gosh, I'm so happy.
Good job. Great work. This is a tough problem. Alrighty, guys. We're going to finish up this unit the next time I see you guys. So we still have a couple minutes left in class, so feel free to just work on something if you guys need to. If you have questions, let me know. But yeah, it's done for today. Good job, everybody.